What if I told you the most valuable resource on Earth isn't oil anymore, and it probably isn't lithium either? By the end of this video, you'll understand why governments are racing to secure rare earth supply chains, why China sits at the center of this competition, and why the biggest geopolitical battle isn't happening in the mines. These 17 elements silently power the modern world. Pull a smartphone from your pocket, and you hold several of them in the palm of your hand. They operate the vibrating motor, the speaker, and the screen. But this is not a story about consumer gadgets. The exact same metals that run your phone also steer missile guidance systems, stabilize offshore wind turbines, and spin electric vehicle motors. They are embedded in the high-speed actuators of advanced robotics, the optical hardware of AI data centers, and the radar of stealth fighter jets. Because these materials are buried deep inside high-technology systems, they remain completely invisible to the public. Yet they form the hidden infrastructure of national capability. Control over these materials determines which nations command the 21st century. To understand the global struggle, we must define the material category. This is a specific family of 17 metals: lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium, scandium, and yttrium. Geologically, they are not physically rare in the Earth's crust. The true barrier is that they are chemically bound, making concentrated, economically viable deposits hard to find. Extracting and separating them requires extreme chemical processing. Within this group, neodymium, dysprosium, terbium, and yttrium stand out as the strategic drivers of high-performance magnets. This is entirely separate from the battery race. While lithium, cobalt, nickel, and graphite store energy, rare earths convert that energy into mechanical power. Why this matters is simple. A battery stores energy, but rare earths make it move. This chemical divide splits the modern resource map into two completely different industrial contests. This mechanical movement relies on permanent magnets. Neodymium iron boron, or NdFeB, is the standard formula for high-performance magnets. These magnets generate incredibly intense magnetic fields, but they face a harsh physical limit. Under high heat, like the 150-degree temperatures inside an electric vehicle motor or a wind turbine, pure neodymium magnets lose their magnetism. To prevent this failure, manufacturers introduce small amounts of dysprosium and terbium. These heavy rare earths preserve the magnet's strength under intense thermal stress. This microscopic engineering delivers a massive industrial payoff. Heat-resistant magnets eliminate the need for heavy copper coils or massive cooling systems in electric vehicle motors, wind turbines, industrial robots, MRI scanners, defense systems, and consumer electronics. Instead, these machines become smaller, lighter, and more efficient. Why this matters is simple. The capability of modern technology depends entirely on this microscopic chemical recipe. During the Cold War, the United States secured its supply of these microscopic recipes at a single site in California, the Mountain Pass Mine. Discovered in 1949, Mountain Pass became the global epicenter of rare earth production, supplying roughly 70% of the world's elements by the 1970s. This domestic mining base secured American leadership in defense radar, guidance systems, and early electronics. Then, in the mid-1980s, China launched a coordinated long-term industrial plan. Chinese state planners treated these elements as advanced assets, funding the entire production chain. They poured subsidies into mining, chemical refining, and magnet manufacturing simultaneously. American operators could not match China's state-backed pricing and lower environmental overhead. By 2002, Mountain Pass halted operations, and the United States let its chemical processing capacity fade away. This change occurred because of industrial policy, not geology. Why this matters is clear. Raw mining is only the first step. When the United States lost its refining plants, global leadership went with them. This raises a fundamental question. Why did owning the ore stop being enough? Mining is only the second step in an 8-stage industrial gauntlet. Exploration, mining, crushing, chemical separation, refining, metal production, magnet manufacturing, and finished high-tech products. The geological act of pulling ore from the earth yields a bulk mineral with virtually zero strategic utility. Real value and geopolitical influence concentrate much further down the line. The pathway from rock to technology hits an expensive wall at chemical separation and refining. This is where bulk ore becomes usable oxide, requiring hundreds of loops of acid leaching and solvent extraction to isolate individual elements to 99.9% purity. This ultra-purification is the industry's greatest bottleneck, demanding thousands of specialized chemical reagents, complex plumbing networks, and capital-intensive facilities. Why this matters is clear. A mine without downstream processing is strategically incomplete. It leaves a nation exporting cheap, heavy raw concentrate while remaining entirely dependent on foreign adversaries to transform those minerals into the high-performance permanent magnets that drive advanced robotics, guided missiles, and electric vehicle fleets. China consolidated this entire sequence inside its own borders. By co-locating separation plants, metal refineries, and magnet factories in industrial hubs like Baotou, Beijing built a closed loop. This physical proximity creates an operational speed that Western competitors cannot easily replicate. It also yields immense geopolitical power. When diplomatic tensions rise, Beijing can restrict exports of finished magnets and raw oxides. In July 2010, a 30% quota cut triggered panic across global industries. Toyota halted hybrid production, and Siemens paused wind turbine manufacturing. Why this matters is clear. The modern economy depends on these exact materials. Electric vehicles, wind power, and artificial intelligence data centers all compete for the same limited supply of neodymium and dysprosium. At the same time, defense modernization programs require these magnets for missile guidance and radar systems. This soaring demand amplifies the risk of any sudden supply cutoff. But the race is no longer confined to Chinese borders. The search for security is forcing Western nations to hunt for alternative sources in unexpected places. In 2022, the United States passed the Inflation Reduction Act, deploying billions in subsidies and tax credits to rebuild its domestic processing base. Allied nations quickly coordinated. Australia positioned itself as the primary non-Chinese supplier, backing Lynas rare earths to expand refining capacity. Canada launched a $5 billion critical minerals strategy to fast-track exploration. Simultaneously, Japan's Ministry of Economy, Trade and Industry funded overseas joint ventures and secured a 6-month strategic stockpile. In Europe, the 2023 Critical Raw Materials Act established targets to source 40% of strategic materials from friendly nations. This shift toward friendshoring and permitting reform is rewriting the supply map. Control over high-tech processing industries determines victory, while raw mining remains secondary. Subscribe for more geopolitical analysis. State financing and diplomatic pacts are targeting new deposits from Canada and Brazil to Vietnam, Australia, and Greenland. From African railway corridors to the Arctic, countries are racing to secure future frontiers. Yet, extracting these elements carries a heavy physical price. Separation plants produce millions of liters of acidic wastewater and radioactive thorium or uranium residues. Managing this hazardous waste requires complex treatment facilities and years of regulatory permitting. Stricter environmental standards drive up processing costs and drag out development timelines for Western builders, forcing nations to choose between strategic autonomy, economic affordability, and ecological sustainability. Under 1% of rare earth magnets are recycled today because separating individual elements from complex alloys remains technically difficult and expensive. Alternative chemistries like iron nitride also fail under the high heat of electric motors. Consequently, secondary supply cannot replace primary mining over the next decade. This reality shifts the entire strategic race. The contest now spans the full industrial ecosystem, from chemical separation and advanced research to component manufacturing. As nations abandon efficiency-driven globalization, control over these complete systems has become the ultimate measure of national resilience and economic security. Digging minerals out of the ground is no longer the prize. Today, true power belongs to whoever controls the industries that transform those elements into advanced technology. The monopoly of the future is processed, not mined. Subscribe for more analytical geopolitics.